Welcome students, and in this video we are going to talk about the eigenvalue and eigenvector methods, okay, to solve for e power at. So basically how to calculate e power at, eigenvector methods, okay, methods. So essentially we have seen that if you suppose that we have this problem, right? X prime equals to a of xt, and I want to solve this problem. Let's say that's your one, and A is given to be a n cross n matrix, okay, n cross n matrix, and we need to solve this one, okay. And to do that, what we were trying to do is this: let's say that we suppose that xt equals to e power lambda t times some v, okay. So here lambda and v are unknown, is a solution of 1, yes. Then so we have showed, this we did in last class. We showed that if you suppose that there is a solution of 1, then you can show that lambda v is an eigenpair, So basically it's a if and only if condition eigenpair, okay. So basically it's a if and only if condition, it actually says that for 1 will admit a solution which looks like this: e power lambda t times v, provided lambda v is an eigenpair. So lambda is an eigenvalue, and corresponding to that you have eigenvector v. Clear? Okay. So if that happens, then e power lambda t times v, that is going to solve 1. Clear? So that's fine. Now the point is this: see, let's say that, and we have seen some examples in the last video. In this video we are going to do this case. So if let's say lambda is alpha plus I beta, that can happen, right? Okay, so it can, the A can have so let's say A is a 2 cross 2 matrix, right? So in that case A can have let's say complex eigenvalue, right, where this alpha and beta is in R. Yes. Now the question is this: how do you deal with this? So let's say this is an eigenvalue with eigenvector. So the corresponding eigenvector is given by let's say v, which is v1 plus I v2. Okay, and why I am putting it in a I am not putting it as a subscript but superscript, because v is a column matrix, right? V equals to v1, v2, vn kind of thing. So basically I want to write it is in if I want to write it in this thing, the column matrix form, then I will write it as superscript, and v1 will look like this: v11, v1n, right? And of course vi will look like vi, vin. Okay, so that is why I am just writing it in a superscript. Okay, then so essentially let's say we have a eigenpair such that lambda is alpha plus I beta, and the corresponding eigenvector is given by v1 plus I v2. Okay, now this lemma is a very important lemma, and we did I am quite sure you guys know this from your second order or ordinary differential equation thing, that if let xt, okay, xt is what? It is some function which is yt plus IZT. Okay, and why I am writing it like this? See, it is essentially xt will look like this: e power this lambda, so it will look like e power alpha plus I beta times v, okay, times v. V is v1 plus I v2. Okay, it will look like this. Now you can see that you can just break it up into real and imaginary parts, and you can write it as yt plus I zt. Okay, so let that be a complex function, complex valued function, value solution of 1, here, of 1. Then okay, so if yt plus IZT is a complex valued solution of 1, then real part of xt, which is given by yt, and imaginary part of xt, which is given by zt, are both real valued. This is very important. Okay, real valued solution of 1. I hope this is clear. So what it is saying is this: let's say that if xt equals to yt plus IZT is a complex value solution. Okay, so here for every t the solution which you are getting is a complex number, okay, for every given t. What it is saying is, I mean, you just look at these functions individually. So basically t going to yt and t going to zt, individual functions, okay, zt. Now these two functions you can actually show that they independently actually solve one, okay, not very difficult thing to I mean prove because of the linearity. So let's just look at the proof, very easy. So let's say, so if xt is given to be a complex valued solution, right? So therefore let's say x prime t, what is x prime of t? Let's just look at it. So it is by definition y prime of t plus I z prime of t, okay. Please remember y, z, these are all column matrices, okay. A is given to be n cross 1, n cross n matrices. So y is a n cross 1 matrix, z is a n cross 1 matrix. So y and z are column matrix, okay. Vectors, if you can, I mean you can say column vectors also, that's not a problem, okay. So xt equals to will look like this, and what is okay, and this is equals to capital A times xt, right? xt is again yt plus izt. Clear? Now you see here, of course, A, whenever we are talking about real matrix, okay. We are not dealing with a complex matrix right now. All our system or all our equations which we deal with in our course are all real systems, okay. So that is the reason why we want our solutions to be real solutions, not imaginary solutions, okay. So x prime t is equals to ayt plus izt, okay, and you can write it like this. So a is real, so essentially if you equate the real and the imaginary part, what will that give you? It will give you y prime of t equals to a of yt. I hope this is fine. A is real, yes, and z prime of t is equals to a of z, okay. This is equating real and imaginary part. I am not writing all that, I think you guys can understand that, right? So essentially then you see what is happening is this. Of course, what is x? If x is a complex valued function, of course it is c1, so it is a holomorphic function essentially, right? If it's a complex valued function of 1, okay, what does that mean? It means x prime t exists, so that complex derivative exists, right? That's what it is saying, and it is equals to a continuous function. So essentially, because A is a it's a square constant matrix, so that's a constant, and x of t, if x prime is differentiable, so essentially x is continuous. So A times xt, this is a continuous thing, so x prime t is continuous. So essentially what you are saying is x is c1, complex c1 is basically holomorphic, right? So x is a holomorphic function, so basically x is an analytic function, that's all, okay. So since x is given to be analytic, of course y and z are analytic functions in that case, right? So essentially the real part of x and the real part of the real part of x, y, which is given by y, and the imaginary part of x which is given by z, they are both smooth, right? Okay, so hence they are smooth functions and which satisfies these two equations. Therefore, you have the solution. So they both solve the problem. Okay. Now you see, as I told you, we have to see what yt and zt is. Okay. So you see, as I told you, this is the function, right? So essentially, you see, so that's done. Let's done. Okay. Now you see, x of t is given by e power alpha plus I beta of t. You see, we did it here, right? Because x of t is e power lambda t times v, and v is what? V is v1 plus I v2. Okay, please remember v1 and v2, they are column matrices which looks like this. Okay, vi's. Okay, now let's just break it up and write it. So if you break it up, it will become e power alpha t, the real part, not a real part, the real number e power alpha t is a scalar, v1 cosine beta t minus v2 sine beta t, okay, plus I v1 sine beta t plus v2 cosine beta t. Okay, so that's the x of t which you are going to get. Now by the equation, by the above lemma, what does that mean? It means that what are the solutions of this thing. So y of t, if you define it to be e power alpha t, okay, and v1 cosine beta t minus v2 sine beta t, this is a solution, okay. And also zt, which is given by e power alpha t, the imaginary part, okay, v1 sine of beta t plus v2 cosine of beta t is a solution. So what sort of solution is it? Real solution, okay. Please remember this thing. I am not going to, so we are not going to be interested in looking at imaginary solutions. Solutions for in our case are always going to be real. Clear? Okay, right. Now let's look at one example and see how we can deal with this kind of cases. Okay, so let's say that example 1, we look at a 3x3 system where A is given by 1 0 0, okay, 0 1 minus 1 and 0 1 1. So essentially, I mean, let me clarify one thing. In most of this ODE system of equations, when we say we are dealing with, let's say, homogeneous system, and in this part we are only dealing with homogeneous system, right? See, given A is enough. Actually, essentially what you have is this problem, right? X prime t equals to A of xt. Okay, so there is nothing special about x. You see, the only thing which distinguishes this equation with, let's say, x prime t equals to b of xt, you understand what I am saying? The only thing which distinguishes this with this is the vector, is the matrix A and B. Do you understand? Okay, otherwise there is nothing, no difference is there. So essentially what is happening is this: if you are just given a matrix, that is enough to, you know, work out the problem. Okay, of course with the initial condition, I mean, if it is given, then it's fine. So in this case it is given to be the column matrix 1 1 1. Is this clear? So basically the equation is characterized only by the matrix itself, okay, I mean, and there is nothing special about it, okay. So let's say that's the equation, I mean, that's the, what is it, I mean, the matrix given to us, okay. Now of course whenever you are given the matrix, I mean, the first thing you do is you look for the eigenvalue. So in this case I am not going to calculate all these things, but I am going to write down what the eigenvalues are given by 1 1 plus minus I. Of course they are in, I mean, if there is one complex eigenvalue, their conjugate will also be there, right? So 1 plus minus I, that is there. Now the thing is, you see, let's look at the case lambda equals to 1. So in the case lambda equals to 1, I mean, you can just look at, you want to find what is an eigenvector. So basically AV equals to lambda V. Okay, so essentially AV equals to lambda V, and you can check that, you see, V1 is going to be 0, right? V1 is going to be, so V1, if you just multiply this thing, it is going to be V1 0 0. So basically V1, and then the second vector is V1 times 0, V2 minus V3, V2 minus V3. The third one is V2 plus V3. So this vector is going to be 0 0 0, right? I hope this is fine. Oh, sorry. This vector is given to be V1, V2, V3. So it is lambda V1, lambda V2, lambda V3. Clear? Okay. So essentially what do you have? You have that lambda is 1. So this is gone. Okay. V1, V2, V3. Okay. V3. Now you can see that if you equate all these things, essentially V1, V2, V3 can be chosen like 1 0 0. Okay, that's the I mean, valid choice of eigenvector. Okay, so in that case, therefore one solution is given by x1 of t. It is given by e power t, lambda is 1 times 1 0 0. Okay, I hope this is clear. Okay, and so this is one value. Now the thing is, I have to talk about e power the complex value. Maybe I can just do it here. Yes, I think that will be better. So case lambda equals to 1 plus I. Fine. Now in that case, what happens is you are basically looking for a non-zero vector, right, such that a minus lambda I, so 1 plus I times v, yes, that, one second, a plus lambda I times v, this is going to be 0, 0 and 0. Clear? So what is a minus lambda, a minus 1 minus I times a? So if you calculate this thing, this is going to be minus I, yes, and 0 and 0, it is 0, minus I, minus 1, 0, 1 minus I equals to, sorry, v1, v2, v3, v1, v2, v3, that is going to be 0, 0 and 0. Clear? Now if you calculate all of these, you see essentially what am I getting is minus I v1 is 0, okay, and minus I v2 minus v3 is 0, and minus v2 minus v3 is going to be 0. So essentially I can choose v1, v2, v3 as some let's say, I mean 0, I and 1, okay, because you see for the first variable is anyways I mean that's going to be 0, right, and so I times v1 is going to be 0, so v1 is 0, and the second two variables we just manipulate it to be I and 1. Okay, so in that case, therefore what is the solution in this case? x2 of t is going to be e power 1 plus I times t, 0, I, 1. Clear? Now what happens is nothing special, you just break it up and you can show that there you get two solutions out of this. Okay, you get two solutions. So the two solutions which you are going to get, I mean let me write it down. So you see, you do not have to do lambda equals to 1 minus I, because you do it, you will get this sort of solution only with some other constants. Okay, so essentially you get two solutions from here. One is, let's say, y1 of t. Okay, let's just write it as y1 of t. It is e power t, okay, and then you have 0 minus, so if you just break, you see it is e power t, e power it, so this is cosine t plus I sin t times 0 I 1, right? This is the thing. Now you just have to break all of this thing up and write it together. So this is going to be 0 minus sin t and cosine t. Okay, so let me just write it down and you guys can verify that if I mean this matches your answer or not. So this is y1 and y2 of t is going to be y1 of t, y2 of t is going to be maybe I can just write it as e power t. Of course e power t is there, and this is 0 cosine t and sin t. Yeah, you just I mean break everything up and we are just writing it together, that's all. Okay, no, we are separating the real and the imaginary variable. Yes, now what is the general solution? So you get three vectors. Yes, do you think they are linearly independent? They are linearly independent actually. I mean, if you are not convinced, you can just check it is going to be linearly independent. That's not a very difficult thing to see. You can take lambda t equals to 0 and all, you can check that they are going to be linearly independent. Okay, so that's not a big thing to do. So since it is linearly independent, hence any solution, the general solution x of t, okay, it will be given by c1 e power t 1 0 0 plus c2 e power t 0 minus sin t and cosine t plus c3 e power t 0 cosine t and sin t. I hope this is clear. Okay, now the problem is not over now. You see, we have, this is a general solution. Now what we want is, we want our solution which passes, which takes the value 1 1 1, the vector 1 1 1 at t equals to 0. Okay, so we are given Now given x of 0 is 1, 1 and 1. Okay, so what does that imply? You just have to calculate what is this. So let's say this is like I mean, from here you see these three, you get these three solutions. So I mean, independent solution, this one and this one. From here you need to find what C1, C2, C3 is. Okay, so let me write down. From here you can actually choose C1, C2, C3 to be 1, 1, 1. Once you calculate all these things, you can choose 1, 1, 1. So essentially the equation, the solution will look like this: e power t 1 cosine t minus sine t, and then cosine t plus sine t. Okay, I hope this is clear. Okay, so this is what C1 equals to C2 equals to C3 equals to 1. I mean, you can choose this one. It's not choosing. I mean, you just put it there and calculate this thing. So once you do that, because it's quite it's quite clear from here. C1 is going to be 1, and similarly C2, C3. You can look it up. It's going to be 1 here. So please check this part, and hence this is how you solve the problems. Okay, now you. Again, I am telling you, don't get confused about what happens with the case lambda equals to 1 minus I, because if you take lambda equals to 1 minus I, the same sort of thing will come with some other constant, minus, plus or something like that. Those will get absorbed with the constant. I hope it is clear. Okay, so don't worry about all that. I mean, from here only we get 3 linearly independent solutions, and actually that spans the whole solution space. Okay, fine. Now, so let me end our video here.